All right. So back to our profiling. So what have we learned so far? The biggest contributors to the total runtime was the grid loop function. It roughly contributes to 1/3 of the total runtime. And my function, which contributes roughly 2/3 of the total runtime. So now we've identified the slow components of our code. And now we can talk about how can we optimize that. Okay, so my function, so let's start with the slowest part. It's my function. And it turns out that's actually fairly straightforward. It's just 2 lines of code. So it's not that obvious what we can do here, right? So that's unfortunate because there's a lot of time spent in here, but unfortunately not much to be gained, at least for now. What about grid loop? Okay, so grid loop looked like this. And that's quite a bit of code here, and it's not immediately obvious where the time is spent here, right? So, I mean, here we're just checking for the size of arrays, so we could guess that that's fairly fast. Here we're initializing another array, that could be quite slow, right? So that's making memory, freeing up memory for 1 million large array. And then, of course, we have the loops, and we know loops are slow. So there's definitely a potential candidate here. But it would be useful to have a more structured way of identifying how much time is spent in each line here. And of course, there's something like that. There's a line-by-line profiler. Right? So the C profile that I showed you before, that showed you how much time was spent in each function call in your Python program. The line profiler module shows you how much time is spent in each line of a Python function. Okay, so the way you use that, it's a module that you need to install. It's called line profiler. And then it provides a decorator that you add to your function that you're interested in. In this case, it's my grid loop function. And then you need to run your program slightly differently. So you use this current prof -l-v command to run your program. But then, if you do that, let's do that. Okay, so I use this current prof command here. Forget about the explanation mark here. It's just something specific to IPython. But then what you get is, again, a seemingly complicated table. And you can, so one thing that we should be aware of now, if you look at the total time, that's actually 4.6 seconds. And that's slower than the original 3 seconds that we measured for grid loop. And the reason is because there's an additional overhead from the line-by-line profiler. But we're not so concerned about that because we are only looking at the relative time spent from each line to line. So the overall time is increased, but the relative time spent in each code line is still the same. Okay, so but the exciting part here is now on the very right column, we have our original source code. You can see the def grid loop with all the different, here the for loops. And then here on the left side, we have again the statistics about that. And here now, these are, I think, in milliseconds. So the most important one here is the time, time column, which tells us how long time was spent in that line, and also the hits line, which tells us how often that line was executed. Okay, so you can see, first of all, initializing this 1 million large array took 18 milliseconds and was only executed 1 time. So there's clearly not too much potential here. But then here, when we come to these for loops, you can clearly see. So the first for loop was executed 1,000 times. The timing spent here wasn't too bad. But then we start hitting into the second for loop. This was executed 1 million times. And again, extracting the coordinates actually only took 0.7 seconds. But then here, doing the execution of the function and the setting the values, this is where the 3.2 seconds was executed. So here you can very clearly see where most of the time was spent, namely in the most inner part of the loop. Or in general, it's the loop, right? That is the evil part here. Okay, so the conclusion of all this exercise now is that we've dissected our code and we've identified 2 lines of code, or well, 1 line of code almost, where most of the time is spent, and that's inside loops, right? And I've just shown you earlier today is that when you work with NumPy, the first thing that you should try is to remove loops in order to get speed. So what did we learn here? How can we improve it? We want to vectorize the loops, right? We want to use vectorization. So this is how a vectorized version of this function, of this implementation might look like. So yeah, so here in F now, instead of using the loop, I use a vectorized version of the grid evaluation. So I could have also vectorized my original myEval function, but it turns out that's because it just calls the sinus function, so it actually works immediately. It's already vectorized. So there's no need to add the vectorized operator. Okay, but so now, of course, it's interesting to see how that vectorized version does. So I use again the So I use again the initializer, same parameters, and then I use the timeit module to time the grid loop function. I use again, I need to use this ugly setup routine here, but anyways. But now you can see the timing, right? We went from 3 seconds to 0.015 seconds. So there's a significant speed up. You can just try it again. Yeah, it's always in that range. Yeah, and then of course, in contrast to our original implementation, if you do the same thing, it'll take some time, but this should again be around 3 seconds. Or 2.6 seconds in this case. So again, vectorization, just this vectorization step yielded kind of a 70 times speed up in this case. Okay, questions regarding profiling? No? Okay, let's start next topic. Today we have a lot of topics. Next topic is mixed programming. So NumPy, right? I mean, so okay. So the point. Well, I guess we just start with the motivation. So we're back to the story that Python is slow for numerical computations, or can be slow, especially if you have. If you use these for loops instead of a vectorized version. And okay, so if you look at the different timings for different implementations, we get that Fortran takes about if Fortran and C++ version takes 1 second, then NumPy is roughly 3 times slower. If you do a Python loop version, then it's around 100 times slower using the NumPy sinus function. And then if you use the standard Python sinus version, then it's even 300 to 400 times slower. And so what this tells you is that at least for functions where you can use NumPy, there's a massive speed to gain moving your Python code to a NumPy code, right? But sometimes we are talking about functions that can't be easily transferred to NumPy, right? So maybe you're not working with arrays, but with other data structures that can't be easily represented as arrays. So then still we are kind of lacking this massive gap from Python to C, C++. And so it's this mixed programming that is the topic of the second part of this lecture, is where we bridge the gap between Python and C and C++. Okay. So just again a motivation why these compiled languages are so much faster. So the reason is because at the compile step, the compiler can look at the code and perform all kind of optimization that Python can't do because it needs to execute the code. It interprets the code. So in C, C++, these compilers perform these pre-optimizations. Also, the compiler knows the types, the data types that it needs to work with. So it can do a lot of optimization just based on that. While Python always needs to work in the most general setting, because the function can take essentially any type. So just some examples that C and C++ would do. It does code inlining, which means that if you call a very simple function, if you have a code that calls a very simple function, then it would actually take the function content and copy it into the code instead of constantly calling a function, which creates some overhead. Loop unrolling, that just means that if you have a loop that only loops over 3 indices, then it's actually sometimes faster to duplicate the code 3 times instead of running a loop, right? So I mean, all these kind of little things that C and C++ does to get your code faster, and of course in Python you can't do that. So Python doesn't have these things. So the overall idea now is that can we mix C and C++ and Python to get the benefits of both worlds? So the idea is, can we use C or C++ for the slow parts in our program, where we know C and C++ can optimize it, but then still use Python for the remaining 95% of the code, where we know that it's not speed relevant, but it's much, much easier and more elegant to code. Okay, so in principle, there's 2 different strategies on how you can do that. You can extend or you can embed Python. So by extending Python, it means that you have a Python program and you make you extend that you extend that Python functionality with libraries and functions written in other languages. So that's actually mostly what we're looking at. But sometimes it's also useful to embed Python into an existing program. So I used to work on a big ocean simulator, which was written in Fortran. And so because it's quite old language, in order to kind of quickly script something up, we would embed a Python program inside the Fortran code. So that would allow us to mix both languages. But we are mostly talking about extending. So extending has kind of 2 main use cases. Either you make additional functions available to Python that are written in C and C++. So we are now talking about C or C++ libraries that have been developed over the last years and that you might want to make accessible from Python. So that's one use case. And the other use case is you have a Python program, you know that certain parts are slow and you want to migrate them to C or C++. Okay? And both are valid use cases that are both very important. So there's a bunch of tools that you can use, and I will want to show you 2 today. But I just want to give you a quick intro on what you could do Okay, so the most hardcore version would be to actually handwrite wrapper code that that bridges the gap between the. So Python is actually written in C, and so if you have a C library, you can write so-called wrapper code that makes your C library a Python module, so that you can load it into Python. And so what you need to do is that you need to, if you call a C library from Python, then you need to take all the Python objects, convert them into C data types, then call the function, then get the results, and convert all the output data types again to Python objects, and then return it and pass it over to Python. So this works very general. You have a lot of control, but it's very, very cumbersome. I used to actually show that in this lecture, but I stopped doing that because it's just not necessary today anymore. So then there's a module called C types that essentially makes that just essentially makes this hand coding that I showed you before a little bit more elegant. But again, it's not something that I show anymore. But so here are the two solutions that I want to show you today. The first is called Cython. And what Cython does is it's an extension of the Python language. So it adds additional keyword arguments to Python and it adds a compiler to Python. And so when you write a program in Cython, you can add types, for instance, and you can also compile this Cython program, and you get a module that you can load in Python. So that's the first one, and we go through an example in a second. And then there's a second one that I want to show you. It's called Numba, and that's a very, very advanced tool that has been only developed in the last 5-10 years, I think. That's a lot more automatic. So we will see that using Numba is often just adding one decorator to a function. And that's all you need to do. But we'll start with Cython. Okay. So as I said, Cython is an extension to the Python programming language. So it adds additional keywords that you can use, for instance, to specify types to the variables that you use in your Python program. But you can also call out to C functions that are implemented in other libraries. So once you've written up a Cython program, you need to compile it. You use a Cython compiler. And once you've compiled it, you get a Python module out that you can load in from any other Python program and execute the function that you've implemented. And so the major advantage of using Cython is that you can do this, you can do code optimization incrementally, because any normal Python module is also valid Cython code. So in principle, you could just take your Python code and apply the Cython compiler to it to get a compiled Cython implementation of that. But the speed advantages you only get when you start adding types, type definitions to Cython. And so this is new syntax that Cython provides. So it's called cdef, which means you're specifying the C type of a variable. And here what you're saying is that the following variables are integers, I, j, and k. And here you have more integers where you say you have floating point values, f. Then here you have actually an array of f with 42 entries. And then you can even do pointers if you want to do advanced C. The same thing also goes with Cython functions. So Cython provides 3 keywords, or actually 2 keywords. So a normal Python function can be defined like we're used to. So any normal Python code is also valid Cython code. So we can just specify normal Python functions. But we can also do something called cdef. And so what that does, and so in our Python functions, what we can do is we can specify the types of the input types. So integers, here's a pointer to character, which is a string. So if we want, we can provide these type hints to Cython. Then sometimes it's useful, maybe you only have a function that is used within the module, but is never loaded from another person. Is never loaded from externally in that module. So then what you can tell Cython, then you can use the cdef, which means that the Cython compiler will only generate the C version, but it will not make it available outside the module. So then use cdef. Again, if you have a type here before the function name, that means the return value is an integer. So x returns an integer, and it takes an integer and a float. And then there's also cpdef, which generates both a C version and a Python version of that function. Okay, so what it does is it uses all these type definitions that you provide to optimize the code, just like a normal C and C++ compiler can optimize your code. So, so in principle, right, you can just write for I in range n. So that's just default Python code, and you don't actually need to change the code. But Cython will optimize this for loop depending on which types you provided. So if you haven't provided any type hints for I and n, then you end up with standard non-optimized code. But if you declared that I is an integer and n is an integer, then this loop will actually be translated to pure C code and compiled as pure C code. And as a consequence, you will also get all the speed benefits of a pure C loop. So this means a normal Python for loop results in a pure C implementation with all its benefits using Cython. So I want to show you an example. Let's say we want to approximate the integral of a function f of x. So how do you do that? Which means that we want to compute the area below this function. The way you do that is you create these little rectangles below that function, and you always multiply the area of that rectangle, and you compute the area of each rectangle and add them up. And then if it's below the line, then you subtract them. Right, that's the strategy. The problem is that the accuracy of this method increases with the width of the rectangles, so you need to make them smaller and smaller to get it more accurately. So very quickly it becomes quite expensive. So it's important to do this fast, especially if you're working in higher dimensions. So if you want to do integration in 2D and 3D, then it becomes really important. Okay, so now what we will do is we will start with a pure Python implementation, and we will slowly convert this to Cython and hopefully see speed ups. So here's a pure Python implementation. This is the function that we want to integrate, sin is x squared. And this is our integrator. So essentially what I do is I want to integrate from A to B using n intervals. So this is the accuracy. Compute the width of the rectangles, which is dx, which is simply b minus a divided by n. Then I loop over all the all the rectangles, and then compute the function at the beginning of the rectangle and add them all up, and at the end I need to multiply by dx to get the correct volume. Okay, but the point here is that I have this for loop where I loop over the number of rectangles. And so now I can run this. I call it from integrate from 0 to 7, and I use 1 million rectangles. And so you can see it takes quite a bit of time. I repeat the experiment 5 times, but on average I get 415 milliseconds per integration. So now we want to apply Cython, and as I told you before, Cython code needs to be compiled. So the first thing that you need to do is you need to rename your Python program to pyx, which is which indicates that we're now talking about the Cython implementation. But otherwise, for now, we don't need to do any changes. We just keep the original Python file. So then you need to compile it. You could do this manually. I've shown the steps here, but it's actually much easier to write a setup file that does the compilation for you. So if you add a setup.py file with with this content here, essentially it's exactly the same as the setup files that you've already written. The only important line here is this ext modules equals cythonize star.pyx. That simply tells the setup routine, compile any pyx file that you find in my current folder. And so then, if you want to compile it, you need to run python setup.py build ext ---- in place. That just means that find all the pyx files, compile them, and place the resulting modules in the current folder that I'm working on. So because I'm working in a Jupyter notebook here, I use this little trick here. I load this extension here, and then I can just use this double percentage sign here to do the same thing. So I don't need the integration now for this lecture here works in place. But so now the point is that I can, so by adding this thing, I now apply the Python compiler. So if I run this code again, it has now compiled it in the background and created a module that I can, or if I now call this integrate fcython function, it now calls the compiled version of that. So of course now the interesting thing is, do we get any speed up from using exactly the same Python implementation, but now passed through the Cython compiler? And so if you're timing it, so remember before we had around 415 milliseconds. So just by passing it through the Cython compiler, we already reduced it to 291 milliseconds. Okay, so the next thing that we can do is I can use there's a magic function called ---- annotate. And if I use that and I compile the function again, I actually get a nice output that tells me, wait, okay. I don't know what that was. Okay, so what this output here shows you is in which lines of the code how much Python code or wrapper code had to be generated because there was not enough type definitions. Okay, so essentially the take-home message is whenever you see something yellow here, there's potential to optimize it using Cython. And so the first thing that we can optimize is by adding types. Okay? So what do? Whenever we create a new variable, I now specify which type it is. So here, S, I know this is a double. This is the sum of the area. So I know this is a double, so I write cdef double S. Same thing here with the width of the rectangles. I specify cdef is also a double. Then I was the index of the rectangle, so I know this is an integer. And that's actually it. So now, just by providing these 3 types, we can check again. Okay, and so you can already see there's a little bit less yellow. And so specifically the for loop here, if we go up again, that was completely yellow before because we couldn't. So here, the for loop is completely yellow because neither the type of I and n was specified. So there was a lot of wrapper code going back and forth. While now, the for loop is completely white, which means that it's translated to pure C code. And so we can actually look at that C code that is being generated, which is here. So the variables are a bit messy, but essentially this is the C code, and this is kind of a 4-line C code that you could compile. So we went from, just by providing these data types, from a pure Python implementation to a pure C implementation. So now we can run it again. And so we see that we already went from 415 seconds to now roughly 186 seconds. But there was still quite a bit of yellow codes. So you can see the f function here, there's potential here. And what else was there? Yeah, so there's this S here. Yeah, I guess these are the ones where you can probably gain the most for now. So let's see what we're doing next. Yeah?
Do you have import special libraries?
Yes. So I can talk. Yeah, I can talk about this in a second. So so I said this f function was, I still hadn't specified types here. So this is what I do next. So I specify that f takes in a double and returns a double, but also the sinus function. So as I said before, in principle, any Python code is also valid Cython code. So in principle, you can keep your original from math import sinus. But the problem is that now, since we've optimized this f here, x is going to be a C double. But if you're importing from math import sinus, sinus is a Python function that expects a Python object. So what Cython will have to do is it takes the C double, needs to put it into a Python float object, execute the sinus function, and then gets its result, and then extract the double out again and go back to C. So you see there's kind of a lot of overhead because you go from C back to the Python implementation of sinus, back, get the result, and go back to C. So that's what you want to avoid. And the way you avoid that is that you load a pure C implementation of sinus. And that's, for instance, one way of doing that is to load the sinus from the libc.math implementation. Okay, so now by doing this, we should be able to see that this line becomes pure C. So there's no going back and forth between Python and C anymore. So we can check it. Yeah, and so yeah, you can see that now our function definition is completely white. And all we're doing is, so the C code that I expanded here is literally now calling the just the C sinus implementation that we loaded up. So we can, we could test this if I remove this again and add the from math import sinus. So now you can see that the sinus line is yellow. And if I expand it, you can see this is all the wrapper code that is going on in the background. And what's going on is it takes this x, it puts it into a Py object, which is a which is going to be a floating point value. Then it calls somewhere down there, it probably calls sinus, the Python sinus. And then at the end, it converts the pi float, that is the output of the sinus, again is a C double, and then returns it. Does that make sense? Yeah. Okay, but let's see. So now let's load the C implementation. We get our nicely optimized code, and we can run it again. And so this is, now we gained quite a bit of speed up, right? So we went from 418 seconds to 22 seconds. 22 milliseconds. Oh dear. There you go. Okay, so and of course the speed ups can be much, much higher, especially when you have multiple nested loops, right? That's when you're really gaining. Okay, any questions regarding Cython? So remember that, so this is a really useful tool when, without having to do much effort, you can very slowly convert from a pure Python implementation to something faster. Okay, so the last part that I'm so sorry about this. This is really... Okay, so the last part is actually the coolest part. I know I only have 7 minutes, but that's enough. So Number is doing essentially the same thing as Cython, but it does it on the fly. So imagine the following. So when you run a Python function, right, when you just look at the Python source code and you have some arguments that you don't know, you have no idea of telling which data types are going to be used in that function, which means there's no optimizations that you can do, right? And that's why Python is slow. So in Cython, what we did is we hard-coded the data types, and suddenly we could benefit from the speed performances, okay? Number now does the following. While you're running the program, when you hit a function, suddenly at that point at runtime, the types are specified because you're passing them as in arguments. So during runtime, we can actually talk about specific data types that are passed to a function, which means that at that point, we can automatically generate the data types, compile, specify the data types, and compile that function as a module and execute it instead of executing the original Python function. Do you see what I mean? So it does the step that you had to do in Cython, it does it automatically at runtime, because at runtime the types are known. Okay, and that's the idea. And that's essentially, once you get this idea, then everything falls out. So you need to install it as Number. And really all the magic, I mean, so because it's so automatic, there's not so much to talk about it, right? So what you need to do is if you have a function that you know is slow, you add this add_chit decorator to it, which is a number decorator. And then that's it. So now when you execute that function, the number_chit decorator will look at the inputs, identify the types, and then compile that function to a compiled version and execute that one instead. So of course the output is exactly the same. So I can remove this, you can add it, and you won't see any difference. Okay, so let's check how much we actually gain. So I define exactly the same function, sum2d it's called, as a pure Python function, so I don't use the decorator. And then we can do a timing. So let's run both. So the original time_it function, so the pure Python implementation, took 416 milliseconds. And now the one where I just added, all I did is I added this add_chit decorator to it. And If I time that, I get 2.27 milliseconds. Okay? So number is Cython automated, so to speak. That's it. Any questions? Yeah?
Do we add the decorator to every method that we want to use it on?
Yeah. So the question is, do you need to add the JIT decorator to any method that you want to use it on? And the answer is yes. But the answer is also, number is really a research project, and it doesn't always work. So in general, number works best on pure numerical code. If you do these kind of numerical computations like this summing up two-dimensional arrays that I've done here. So your best strategy is to first do profiling, identify the slow parts of your code, which are probably going to be kind of heavy numerical parts, and then apply number only on that computationally heavy part and leave the rest as pure Python.
I was wondering what you can have parameters on the JIT decorator that's no Python.
Yeah, so the question is, JIT has some parameters you can add, and they're essentially optimization flags. One is called no Python. I'm actually not entirely sure. I'm not entirely sure about the details, but I think what it does is, so number tries to convert your code to C code, and if it fails, if certain parts are not supported, then it just uses the original Python code as a fallback, which means that then you don't get any speed up. If you add this no Python flag, then you get an error message instead. So then it really tries to convert it to C code and it fails, then you get kind of some warning or error message instead. So then you might need to change your code in order to get it number compatible. But so again, so this important thing here, so number and NumPy are somewhat separate, right? So the strategy of number is that you can keep the loops. If you use number, you don't necessarily need to remove the slow loops because they're going to be translated to C, right? So NumPy is kind of a different strategy where you say you remove the loops using the vectorization. So if you use NumPy, if you already use NumPy, you probably don't gain so much by also using number. So you kind of choose one or the other, but not necessarily both. Any other questions? No? Then see you next week.